Good evening, all. Welcome to live session number 12 of Computational Fluid Dynamics for Incompressible Flows. We'll get started in a minute. Yeah, it's 5 o'clock. So I think we'll get started now. So myself, Durga Prasad. So this is the last session for this particular course. So this week, the discussion is mostly on simple algorithm, which is used to solve the Navier-Stokes equation. So we will discuss simple. We will see its implementation using Julia for a 1D problem. And then we'll also discuss some previous year problems for this particular using in this particular case. So let's say have 1D problem just like before. The governing equation will be or yeah, so you have the continuity equation which is del d dx of u times a is 0, and then we have the momentum equation which is d dx u. Let's assume area is also constant for now. We will also solve a problem with variable area cross section, but for now we will say we will take equations where you have constant area of cross section. So the momentum equation is the advection term is diffusion, and then we have the pressure gradient term. So these will be my governing equations, and accordingly I'll also have the boundary conditions. So for now we will start with the governing equations and how we discretize them. So last week we solved the same problem, but wherein we know the velocity u explicitly specified to us. So the equation is something. The last week when we were solving, we have a general scalar transport equation of this sort, this kind, something of this sort plus some source term. So now what we are having is phi is now replaced with u, and this is basically my source term if you were to compare these two equations. But the main challenge that comes here is this equation, when u is already known to us, is actually linear. However, here this is a nonlinear equation. So which means we have to come up with some different way to solve the same set of equations. The discretization is same as before. We have the grid as, let's say this is my domain. We divided it into cells, and then we have cell centers, very similar to what we did for Mach algorithm. So these are my cell centers, these are my phase centers. So just like when we did using Mach algorithm, we already observed that there is this problem of checkerboarding when you use a mesh that is kind of like if you store velocity and pressure at the same values, then what would eventually happen is you will have the checkerboarding problem. We discussed this extensively when we were discussing Mach algorithm in week 7, I guess. So I'm not going to that again. So the idea is, again, we have to use a staggered grid, which means I have to use the two different kinds of discretizations. One will be this. So one will be, I'll consider this as my cell and then do discretization. Similarly, I'll have to do another one, is another half cell, this one. So the second half cell will actually be used for the discretization of momentum equation. So this will be the cell used for momentum equation, and this will be the cell that is used for continuity equation, just like what we did in the Mach algorithm. So what happens now is we'll start with the momentum equation first. So the discretization is same as before, but as I said, since it is non-linear, we have to first linearize these equations. So So when we kind of do the discretization, we will end up with having a set of matrices. So this equation will become something like D, where D is the matrix, or I'll write it in the standard form that's familiar to us. So if you do the integration, here it will be U east. So continuity equation should be discretized across the cell center. So this will be the cell for which I'm doing the discretization. So it will be u east minus u west. Like we are doing FPM, so integral d dx u from equals to 0. This will give my u east a east minus u west a west equals 0. So this is basically my f east minus f west equal to 0. This is the equation we'll get from the continuity. Similarly, we have to discretize the momentum equation, but the momentum equation will be discretized in a staggered cell, which with the center at the east face E. So if we do the same here, because I'm doing the discretization here, it will be between xp and xe. So expanding the term is very similar to what we did for the advection term last week. But assuming again, we will assume now, because the originality equation is non-linear. So to linearize it, we have to start with some assumption here. So where we say that this particular term, we will write this as f east u east f west u west. This everything is same. So this is very similar to what we did last time. So d east times u east minus up. We are doing discretization like this. So at this phase, del u del x will be between these two cells. So let's say this is east east. So the diffusion, the d coefficient will be calculated at e point, and then I have these two cells to be taken into account. So this will be u east east minus u east. Similarly, for the west term, I have minus dw. For this particular cell, if I do the discretization, it will be between. So this is my cell. This is the west face for that. So it will be between these 2 points. U, sorry, u east minus uw, and then I have the pressure term. So this is again we will use the mean value theorem. So this area we will approximate with the mean value at this particular phase times del p del x. We will use so this is basically we are treating this as a source term. So where del p del x is the gradient at this particular point, which we will write it as p east minus gradient at this point is between two neighboring flags, like use a central difference scheme. So pe minus pp. So this will be the equation. Then again, depending on different schemes we have, this Fe UE can be written in different ways. If you use affine scheme, U east will be like because U is stored at the phase centers. If you use a central difference, it will be the sum average of these two quantities. If it is affine, depending on the flow direction, it can either be this or this. So when you consider all of that, we can eventually write this in a form where you have my current cell is E, so I'm writing AE UE as the summation of this plus whatever the pressure term we have here. So this is the equation we will be getting from this. And from the continuity, we have this equation. This is from the momentum equation. So just to kind of make it easy to understand, eventually what we will be doing is we'll have to convert this into some matrix, and then we'll be solving the set of matrix equations. So this can be written something like some matrix A times U. This is some constant. I'll just take it to LHS. This will be something like A times U plus this will be some matrix B times P equals to 0. And this can be written as basically, this is also some constants getting multiplied to the U velocity. So this is some matrix D times U equals to 0. So this will be my one equation and this will be my second equation. So essentially what we are trying to do is solve this set of equations. But the only challenge now is A here, like in the last week when we were discussing, the matrix A is basically it has the DE and FE and all these terms, and all these terms have velocities in them, and velocity is known to us. So this is basically a linear system in the last week. So all we have to do is just take it on the LHS, RHS, and we'll be able to, like, this is a source term. You can use Gauss Seidel, TDMA, whichever algorithm you do, or do a matrix inversion and then calculate you direct solve for whatever your phi is. So previously this was phi. But now the problem is, because A is a function of u, just to say that, I'll write this as, say, I have two equations. One is this, and because A is a function of u, I'm writing this as AU, the subscript, just to say that this is a function of u. B again is not a function of anything. So P here is basically this area, like it could be function of X, and then we have P minus PP. So this A B matrix will be something like you have a minus 1 1 0 0 0 0 minus 1 1 0, so on so on. So this will be the matrix P, which is not a function of U. So I'll write B as some constant times P is the pressure that we are trying to solve for. So these are the set of equations that we are solving, which are nonlinear in nature. So how do we solve that set of nonlinear equations? The usual way is, say if you have a set of nonlinear equations of u comma p equals to 0, and we are trying to solve for u and p. So the way we start out with is, we will assume some values. So you will get some values of u comma p, and then you do some iterations where you'll update the value of u, saying u, let's say u double star is the next update, such that this is u star plus some delta u. Similarly, p also you'll update, and then you keep doing this till whatever criteria is satisfied. And the criteria is basically you have to satisfy our set of equations, which is d times u equals to 0, or basically my new values are u double star and a u double star plus. So the residue of these two terms should be within whatever tolerance you want. Until that time, we have to keep updating these values. The only problem now is, sorry, so this is delta p. So the only question now is, we start with an initial guess, but we still have to figure out what is this delta u and delta p are. And depending on, there are different ways to calculate this delta and like how to update from given velocity to the next velocity, and then you keep iterating. So how to get this delta u and delta p, there are different methods. The one that we will discuss today is simple. This is one method out of it. There are several methods, or other methods also. So in simple, the idea is again just as before. So we will start from this equation where we will assume a pressure field. I'll just say assume some pressure field, and we also have to assume some velocity field. So these will be the initial conditions that you will give to the algorithm. Then what we will do is, from this algorithm, from these values, I'll have to calculate a value, because a is a function of u. I'll calculate AU star from that, and I do not know the U value. B is something, again a constant, which we already know, which we can calculate. It only depends on the boundary conditions and nothing else. AU star again is, again, once you know the material properties and how area etc. vary as a function of x, AU star can also be calculated. The only thing is U, which we do not know. So I'm assuming initial velocity, and with that velocity I'll calculate all my coefficients first. So from this we'll take P star is a guess value that we have, and this is the system of equations I will solve. So because u star is a fixed value, A is now a matrix of everything is constant inside this matrix. So this is again a linear system of equations, which I can solve. So from this I'll solve for u. So let's say u will become some u double star or something, where this u double star is basically minus A star inverse times B times P star. So I'm writing inverse, but you don't actually have to calculate inverse. You can use Gauss Seidel, indirect or direct method, any other method. The idea is you are solving this system of linear equations. So from this we will get u double star. So one equation will get satisfied. Of course, it is still not continuously satisfied. So we are doing it in a step-by-step process. So where initially we'll get some velocity u double star such that it satisfies this equation. So u double star will satisfy this equation, but still we have no guarantee that it will satisfy the other equation, the continuity equation. So that should be the next step. So we have to now change this in such a way that it will satisfy the continuity equation also. So what we will do is, we will assume that let's say u tilde is some velocity, which is u star, u double star, whatever I got here, plus some correction. And I'm doing this correction such a way that d times u tilde, which is d times u star plus d times u prime, is 0. So I'm saying that the velocity that I got here did not satisfy continuity equation. So I have to change this velocity by updating it with some correction, and that correction is u prime. So I do not know what the correction is, but whatever be the correction I am adding to u double star, which will give me some new velocity u tilde such that the new velocity u tilde is divergent free. So that would be this equation. But still, in order to solve this equation, I still need to know. Now I have like basically we have one unknown. Now I added one more unknown u prime. So I need one more equation that relates between u prime and these quantities. So for that, what we will do is we'll take this equation, the original equation a u star. We already know the solution where u double star will satisfy this equation, which we already know. Now what I am saying, the new pressure at for which the next iteration that I will be doing will also have to satisfy this equation. So let's say a u star times whatever new velocity that I am getting. Of course, for the new velocity u tilde, the pressure need not be the same. The pressure will change. So the new pressure p double star, and I can take the difference of these two equations, which will give me and just like this difference I'm calling u prime. Similarly, whatever is the new pressure I'm getting minus whatever is the current pressure. So I'll call that as pressure correction p prime equal to 0. So this is basically my pressure correction equation. Or we'll get there a little later. So this is not actually pressure correction equation. So now we have to solve this equation again. So there are several ways to simplify this equation. One way is, so this is essentially again a big matrix that we have. So this can be, you can use TDMA or something, and somehow you have to get a relation. So now here is where simple does some, we have some simplification here where we will assume that the contribution from the neighboring term is not present. So this usually when we have is, this AU star will basically have some minus AP, A east, all zeros, or this is something like this, and then you have minus A west, AP minus A east, 0, 0 minus A west. So it will be some TDM tridiagonal matrix for a 1D problem. So in the tridiagonal matrix, everything else is 0. So what we will assume now is we will only consider the diagonal elements, because we know that this will have to satisfy Scarborough criteria, and it has to have the diagonal dominance, etc. So the contribution from the neighboring terms, like the diagonal term, is much higher than the other terms. So we will neglect the other terms, which is, of course, when we do the neglection, it means that we are breaking the physics somewhere. So which means we cannot directly, u prime is, loses its physical significance directly. So that's why we'll do more iterations. We will use some under relaxation or something and then do more iterations. So, but so what we are doing is, instead of solving the full equation, now we will say that we will only consider another matrix. I'm calling that as A prime, which is constructed only from the diagonal elements of A star. So all the off diagonal elements, I'm making them 0. So I'll only take the diagonal elements of A star and call that AU prime. So this is basically then becomes a very simple equation to solve. So like I'll call A diagonal or something. So then I can write U prime as minus this. Okay, I'll call it A prime. So let's just use the same notation. A prime U star inverse BP prime. So this is the equation for U prime. So this is simple matrix now. This is a diagonal matrix. So when you have a diagonal matrix, taking inverse is straightforward. All you have to do is just take the reciprocals across the diagonal, and that is how you get an inverse matrix. So this will be some simple operation. Instead of using TDMA or something, this will be way faster. Now once I have U prime, I can substitute this back into my equation here, which will give me d times U prime is minus d times U double star, because we are assuming d times U tilde equals to 0, because the new velocity that we are getting should be divergence free. And U double star is already known from here. I can substitute this into this one, and U prime is also known to me. So I can write this as d times A prime U star inverse B P prime equals du double star. So all I have to do is do an inversion again here. So this is again another equation that we'll be solving, from which I can obtain P prime. Once I get P prime, all we have to do is P double star is whatever previous case I have plus this correction. Similarly, once we have this P prime, we can substitute in this equation, get U prime, and then I can update my U also. So U triple star will be whatever is the velocity I got before plus this correction. Now the question is this U, so the new velocity and pressure that I'll be having are U triple star and P double star. So these two values again should have to satisfy this equation. So this here we'll have the triple star, U triple star, which will satisfy continuity by default because we are ensuring that this is satisfying continuity. But the question is, with this U triple star, now this A will also update now. So A will become, so this equation will be satisfied. So D times U triple star equals to 0. This will be satisfied because we are ensuring that it is satisfied. But the next equation where you have A U triple star times U triple star times whatever is the new pressure I am getting, this equation may or may not be satisfied, which means now again we will have to update U triple star again. So because this equation may not be satisfied always, now with the current P double star value, again we will solve for a new U triple star. So this will become U4 star and so on. So when the new U4 star will come, again continuity may not be satisfied. So you have to again repeat this thing. And then you have to keep doing this till eventually you reach a point where the U will satisfy both these equations. After, like, the nonlinearity will also kind of get involved into this. So eventually you reach a system where you will have the U equals to 0, and the same U value you take, compute your coefficients, U plus BP equals to 0. Eventually you will reach this thing. So this is in the simple way. So this is a simple algorithm. Now, as I said, the other alternatives also, there are other ways also to go about this particular problem. First one, if you have observed here, is I started out with an initial guess for U. U star is my initial guess for U, but I've immediately overwritten the values of U star. Once, like, the pressure values are what are being taken care of, but U star, whatever, even though I gave a very good initial guess, all that is being used is to compute the coefficients. But immediately after the next iteration, all of them are getting gone. Like they will be rewritten. So what the other way to go about is simpler. Again, the trick is same as before. So you have the same set of equations. But we will do a little rearrangement here. So I'll write this equation. I can also write this equation in a slightly different form as something like this. Say, I'm basically adding and subtracting U. What will I get from this is, now when I assume an initial velocity, I'll assume an initial pressure, but we are assume the whatever initial velocity that I'm assuming, such that let's say D times U star equals to 0 is satisfied, let's say, but my pressure field is not correct. So if I substitute U star and the corresponding P star, this is not equals to 0. So whatever, so you don't have to worry about giving the pressure field, because giving a pressure field is always difficult. So what we can do now is, now we have to solve for P star separately. So we know the values of U star, so we are trying to solve for P star now. So again, the idea is same as before. We have to use some kind of simplification where you will divide it into two forms as this. Then now we have to use the guessed values, and so I'll read this as I times U. This one I will leave as it is, and the second term I'll make this as U star. I already know the U star value. I'll write this as P or P double star or whatever, P double star. Because I know P star is not the correct one, so I'm trying to solve for P double star. And we know that du should be 0. So I can multiply this equation with d, so that will give me du. So this will be 0, and this will be the equation I'll be solving for. So P double star will be U star is a known quantity, A U star can also be calculated. So this will give me a pressure. So once we have the pressure, and this pressure will satisfy this equation, P double star will satisfy this equation. But if I take this equation, whatever P double star I got plus this equals to, will this be equal to 0? So I'm using the U star velocity that I have, and like whatever guess velocity I have given, but I have updated the pressure using continuity equation to get a field that is consistent with whatever velocity that has been given to me. So, but will it satisfy this equation? Because if you see, while calculating P double star, I've made a, I've kind of did not solve this equation directly, but instead I made a little rearrangement here where I removed certain component of a velocity and then I solved only for the remaining component. So that is kind of, because of that simplification, this P double star will not satisfy the original equation. So this equation will not be equal to 0. So I have to kind of again solve this equation. So so for a given U star, this equation will not be true. So I'll have to get a new velocity here, some U double star or something that I will have to solve for. This is again a linear equation. A U star is already known to me. So this is some constant matrix. This is another constant matrix. P double star is also known. So this is like basically Ax equal to B that we are solving for. So from this we can get U double star. But again, just like before, once we get U double star, that doesn't mean that D times U double star is equals to 0 will be satisfied. So this may not be true. So now I have to again do the pressure correction just like before. So whenever you have a velocity field that is non-conservative or a velocity field which is not divergence free, then all you have to do is do this pressure correction term. So what we will say is again we will introduce some new velocity u tilde, which is whatever U double star I have plus U prime, and then whatever is same. So this U tilde we will say it is divergence free plus D times U prime, and everything is same as before. So again we'll write the same equation, we'll get the same matrix like this, and this is everything is same as before, but the only difference now is again you'll get an equation for P prime, solve for P prime, and then you'll solve for U prime. Once you have P prime and U prime, you update your velocity U tilde, which is U double star plus U prime, but you do not update, or maybe I should say need not. Even if you do, it would not be any problem. But why do we have no? Why don't we need to update P again? Because in simpler we are starting, even though you are giving some initial guess, like it will again go to here the first step, where even though you do not give any P star, it is anyway recalculating P star from this equation. So there is no point in correcting it anyway. Even if you do some correction here, that correction is anyway not going to be useful, because it will get overwritten by solving this equation. Whatever the momentum equation solves for that particular velocity, that is the pressure that is going to remain. So there is no need to update the value of P again. All you have to do is just do the velocity update. So the only so the difference between simple and simpler is, in simple we started out with a given velocity, given pressure field. So we, like, even though you gave both U and P, we are calculating a velocity field that is consistent with the pressure field. In simpler, what we are doing is we are doing just the opposite. So you are taking the velocity field and using the velocity field, like it is a divergence free velocity field, we are calculating the pressure from that, and remaining everything remains the same. And then we have one more way, again that is also like all of these different methods is basically in the tricks to solve this equation. So when we have the velocity correction term, so this is the equation I'm having. So this, instead of doing it as a TDMA or something, this is where you have, this is one of the computational intensive steps. This is basically called the pressure Poisson equation that we are trying to solve. We already saw last week what are the problems with these Poisson equations, why the error can actually decay slower, and there are different tricks also to do that. We discussed multi-grid method also, how to kind of speed up the convergence of these such equations. So one in simple and simpler, what we did is we just use only the diagonal elements, assume that everything else is zero. And then there is another algorithm called simplex, which just goes one step ahead and it says that okay, you do not have to neglect all the terms, like all the neighboring terms. Instead of treating it in this way, you only update your coefficient accordingly. So because you're in simple, what is happening is we are these elements which are not zero, we are making them zero. So we are losing some information, so which might cause divergence or something. So what we do is we do not take this update. So when I am doing the next update, say u double star or u tilde, whatever I'm using, u tilde is u double star. I won't directly use the u prime, but I will use some kind of something like this, 1 minus alpha into u double star plus some alpha into u star. Similarly, pressure also I won't directly use it for updating. We will use some under relaxation so that we can control the stability of the algorithm. So I have to use a very low value of alpha. So instead of doing like that, what simplex does is it directly updates the diagonal elements. Instead of taking the diagonal elements, it changes the diagonal element itself. So either you are reducing it here or you are changing the diagonal. Either way, all you are trying to do is make it converge faster, or sorry, make it converge in a more stable way. Yeah, this is with respect to the three algorithms. These are the main algorithms that will be used for study case problems. If you are into OpenFOAM, Fluent or anything, this is default algorithms that you will be finding in most of the softwares. And then there are other algorithms for transient, which are not covered in the lecture video, so I'm not going through them. So to those of you who will be appearing for exams, so these are some questions taken from previous year pertaining to simple and stuff. So the level of questions will also be similar to whatever this level is there. And I think it's also already been shared in the discussion forum, and I'm kind of reiterating here that most of the questions that you will see in exams will be directly from the assignment questions that you solve. Around 70%, I guess, 60 to 70% will be the questions that are directly taken from the assignments that you have already solved during this week, that the weekly assignments that you are solving. And you can also go through the YouTube videos that I have uploaded, the recorded lectures. All these questions are taken from previous year problems only. So to those who are preparing for exam, this should be sufficient material. Okay, coming back here. At a given pressure boundary, the pressure correction, okay. So we didn't discuss about boundary conditions, okay, when we solve the question. So at a given, so what we are doing is, let's say I have a pressure P. So P star is my guess. We are doing some correction so that this will be consistent with the velocity at that particular point at that particular iteration. So if you have a boundary condition at the pressure, if you have a boundary like this, and at the boundary, the pressure value is already specified to you. Let's say the pressure is atmospheric pressure. Something like this is already specified. So which means this is not going to change. The velocity has to change according to the pressure and not the other way around. So P prime should actually be zero. You should not do any correction whenever the value is specified at the boundary. The same applies even for velocity. If you are having a boundary like a no slip condition or something where velocity has to be zero, the velocity correction will become zero at those boundary conditions. And why do we need them? Is you see the matrices here. Uh, yeah, this matrix when you are solving for u prime. So this is the matrix you will be solving for P prime, U prime accordingly. So this D, AU prime, B prime and all these things require boundary conditions. Depending on the type of boundary conditions, this value will change. So when I say P prime is 0, I mean P prime is 0 at any boundary condition, the corresponding element in the matrix should become 1. So if I have something like this, these are my P primes. For this particular element, wherever that diagonal element comes, that should be equal to 1. And on the other side, it should be equal to 0. So this is what we did for Dirichlet conditions. So we are not actually solving for that member. So that will be equal, the coefficient will be equal to 1 equals to 0. So that's when you write it as an equation, it will become P prime equal to 0. Okay, question number 2. Mass flow rates across control volume phases can be calculated without any interpolation for the relevant velocity component on a staggered grid. What do we have? So this is my domain. So these are my phases. So when we are calculating mass flow rate, like Fe, basically rho UE times AE. and all these values are calculated like when you so we have only two kinds of discretization. For the continuity, we are doing discretization on the cell. So when we are doing that, we are the phases will be east and west. So the equation is Fe minus Fw, and both are calculated only on the phase centers. So you don't have to do any interpolation. Now, when we are doing momentum equation discretization, which is across this cell, then I would require F capital E and Fw and so on. So there we have to do an interpolation, but not for the calculation of mass flow rate. This can be calculated directly. And how do I calculate Fe and Fw? That is very simple. So you say F capital, if I want the flow rate at this point, I'll have to do is take average across Fe, the neighboring cells. Similarly for Fw, if I wanted this, I can take average of, sorry, this cell. So Fp, this will be Fp. So this will be equals to the neighboring cells Fe plus Fw by 2. Just to kind of reiterating here, upwind scheme or central difference, all these different schemes are for a different thing. So we have Fe times Phi. This is when you have the product of this term, that is where the transport is happening. There is Phi is the quantity that is being transported because of the mass flux F. So that is where you have different schemes. You can write this as Fe times, this is the central difference scheme. Or in the upwind scheme, we have Fe positive. If Fe is positive, then you have P. If P is negative, you have Phi. Something like this. This is upwind scheme. This is central difference, and we have different schemes. Now, all those schemes are only with respect to the values of the Phi that is being transported. In the Navier-Stokes equation, Phi is basically my velocity u. So when you want to implement upwind scheme in, let's say, simple or anything, the flow rates are again calculated using this only. Like you don't do any another upwind or anything here, and all of these are based on the velocity at the previous iteration value. So all these flow rates are calculated from the previous iteration values. So I'll maybe use star or something. So it will be some, let's say Fe star times UE. If you have a term like this in your equation, sorry, in the momentum equation, let's say if you're discretizing on this phase, so we'll have something like F capital E times U capital E. So what we will do is you use the previous values, previous iteration values. So I'm just keeping a star here. So Fe star should be calculated at previous iteration values, which will be average of previous iteration times UE. This again will change from which scheme you're using, either upwind or central difference or something, whichever you want to use. So if you're using, say, an upwind scheme, then UE will be equals to, so this, if positive, negative, and so on. If it is upwind or if it is central difference, you take average of these two and then substitute that here. But this will always remain the same. Here you don't do any kind of upwind or something. So this is just the mass flow rate. Okay. So coming back to the question, as I said, like the flow rates are calculated, like the velocities are stored at the phase centers, and flow rates are also calculated at phase centers. So we don't have to do any interpolation in a staggered grid. Collocated grid calculates the pressure gradient term in a coarser mesh. True or false? So what happens in collocated grid is we have both the pressure and velocity are both stored at the same cell, so that is a collocated grid. So and when we do the minus del P del X term at this particular center, it will end up having P minus PW by delta X. So this will be my pressure gradient term. So it will get approximated in some form like this. So when it is getting approximated some form like this, so basically this is in collocated grid. When we have a staggered grid, if you remember, we are doing discretization on this cell. So the pressure gradient at this is central difference of these two. So that will be PE minus PP by delta X. So this is a staggered grid. sorry, this is 2 delta x. So the difference between these two is, again, here the difference is done on a much coarser size. So it is taking these two cells. So alternate cells will be used. So the delta x, there is a difference of 2 delta x compared to staggered plate. So compared to staggered, collocated is actually doing the discretization on a coarser mesh. I think this is clear. Okay. Which of the following is or are the differences between simple and simpler algorithms? Simple does not require pressure correction, whereas simpler requires a pressure correction. So there is pressure correction. Simple has a pressure correction in it. So just to reiterate here, we have simple, simpler. You assume a P star. From that you calculate U star, and then you solve the pressure correction equation, get P prime. From there you update U prime. From this you get new velocity and pressure, and then you do the same. So this is simple. In simpler, we start with a velocity field, solve for the pressure. Once you have the pressure, then we'll have to update my fluxes and then calculate, get the equations for P prime, solve the pressure correction equation, get the new velocity, and from this velocity again you will update your star. And from U star you will calculate P star. There is no separate P again getting calculated here. So this is simple and simpler. So first statement says that simple does not require pressure correction, but we have a pressure correction P prime that we are solving for in between. So this is false. Simple starts with a guessed pressure field and simpler starts with a guessed velocity field. So that is consistent with whatever we were discussed before. Simple does not require pressure correction and simpler does not require velocity correction, which is kind of false because both simple requires a pressure correction and simpler also requires a velocity correction. Simple starts with a guessed velocity field, which is incorrect. Simpler starts with a guessed field, which is also incorrect. So only one is correct. But of course, you can have multiple correct in your exam. Which method attempts to approximate neighbor corrections using the cell correction while solving Navier-Stokes equations? So if you recollect, we have an equation of sort something like this that we are trying to solve, and several simplifications. And this is some tridiagonal matrix for a 1D problem. If you have a 2D problem, it will be some other structure. It will be pentadiagonal or something. So you have some banded matrix structure for this. And we in simple what we did is we only consider the diagonal elements. In simpler we made also we did the same. So the only algorithm is simplex, where we alter the coefficients of the diagonals by using some correction term, which is again discussed in detail in the lecture video, which I'm not taking up again, but you can go through the lecture video. If you have any doubt, we can discuss that. Okay. In the simple algorithm, when velocity is specified at a boundary, let's say this is the boundary and velocity is specified here, which of the following options correctly describes the boundary conditions? B is the boundary, so this is my boundary, and yes or northeast south cell faces. So which is true when the velocity is specified at the boundary? So as we discussed before, when a particular quantity is specified at the boundary, the corresponding correction for that particular quantity has to be 0. So because velocity is specified at this boundary, let's say u is specified as u naught or something, then we should not correct anything near this boundary. So for that corresponding boundary, u prime should be equal to 0. And the equation, if you are using simple algorithm, we have the u prime is minus dE times the corresponding difference. So if you apply the boundary, it will be some delta p. So if I write it in the matrix form, so u prime is some matrix C times p prime. It will be something like this. So if u prime is 0, the corresponding this will actually be turning into something, some constant times del p prime. Some equation like this. So you can also there are other algorithms also. The major thing here is whenever you have a velocity field, which is not divergence free. So del dot u is not equal to 0. So you're trying to change, you're trying to get a velocity field which is divergence free. So one trick to do that is you always add some new velocity field as whatever velocity you have plus some scalar field w. W can be any scalar field. So del w will be the vector. So all we have to do now is we have to make u divergence free. So the trick is you always do something like this. So you have to solve this Poisson equation. So once you solve this Poisson equation, you will get the w value. You can use the w to make your velocity divergence free. So this del w is what we are calling as u prime. My correction, whatever we are having. So if u prime is 0, then the corresponding the gradient of that particular scalar field should also be 0. It is first option. So but the trick is this. As you can see, another thing is I'm just saying w can be any scalar. It doesn't have to be like, it can be any scalar. The only thing that matters is the gradient of that scalar field. So because we are dealing with incompressible flows, pressure doesn't have any meaning in solving the problem. So all that is important here is the pressure gradient. We are not worried about the actual pressure value. It's the gauge pressure or the pressure gradient is what is important than the actual pressure value. So this applies here. Okay. The pressure term in the discretized y momentum equation for cell center P on a uniform grid is. So in the y momentum equation, the pressure term will be minus del P by del Y. And if you're doing an integration, so just draw the cell. So we are doing discretization for momentum equation. So my half cell should be this, should be staggered from the main cell. So this will be the cell that I'll be doing discretization across. So my integration limits for y will be between yp to yn. And then we have the volume of that cell element, which is let's just write dy dx. So how will del p del y at this particular point depend? So del p del y at this particular point is pn minus pp times the corresponding delta x. I think something is off here. Okay, none of the options are. So I'll just get back to you again. I think I might have there is some typo or something. I'll update in once I upload in the Google Drive. Because once you do a discretization on staggered grid, it should be something like this, which will give me pp minus pn times delta x. But if instead you are doing across the cell center, if the discretization is for this cell center, then you have north and south. So the same thing, the limits will be between y south to y north minus del p del y dy dx. So this will become this will become minus del p. So between minus p north minus p south times delta x. Or according to this one, it will be ps minus pn times delta x. I think it's because the question asks that you do the discretization for this cell, not the staggered one. The option is ps minus pn times delta x. But anyway, I will also check it, cross check it again. In simple algorithm, the correction for v velocity at the north face center of the main control volume P is written as. At the north, so this says that you do the discretization at the north face center. So this is my north face center. So I will be doing discretization across this. Okay. So this is again. So you have a del P return. So the equations are For V velocity, it will be Vn prime, sigma An B Vn B prime, minus you have instead of A naught, I'll just write it as this is delta x. Del P del Y will be Pn prime minus Pp prime. So in simple, what we are doing is we are assuming this contribution is 0. This is what we, when I did that off diagonal elements, all the off diagonal elements are made equal to 0. So there won't be any A and B terms. All of this will be 0. So Vn prime will be, look, there is no minus. So Pp prime minus Pn prime times delta x by An. You see, once you kind of understood the flow of how the algorithm works, all these questions are straightforward. Okay. The discretized continuity equation for cell center P on a uniform two-dimensional grid can be written as. Now, the last two questions are for the momentum equation. So this is for the continuity equation. So again, the domain is same. And continuity equation is discretized on the cell centers. So my equation is del u del x plus del v del y equals to 0. And I'm doing integration from west to north, west to east, and north south to north. This is also straightforward. Del u del x will become u times the difference times delta y. So we are doing it for this particular cell. So del u, the gradient at the east face, del u del x on the east face will be the difference between these two. Times the corresponding area. This is the one outgoing minus whatever is the incoming. So that del u del x at this particular phase will again be the difference of the neighboring cells, so which is up minus uw, sorry, plus delta y. Similarly for the other direction, we have we are doing a mistake here. Okay, on this face it will be minus I gap, so you have a minus here. So on the north face it is again del v del y is vn minus vp times delta x, and in the other direction it will be x. You can now write it on the other side for up and vp. So you have vn minus vs, ue minus u west, and ue minus u west should be with delta y, and this should be with delta x, and this should be minus between them. So this is not correct. So this is the one. The value of V naught for the no slip condition at the wall for the uniform grid arrangement as shown below is. So this is slightly different. So when we were solving in the last week, we did the half cell method. So when we want to read the boundary, we only integrated for this half cell. That is how we did in the last week. So there is another way to go about it is you take a ghost cell, like add one more node again. And then what we have to do now is we are saying that this is a wall. So velocity here on the wall should be 0. Then we will use an linear approximation between these two. So velocity at the boundary, let's say Vb, is V plus the ghost cell velocity V naught by 2. And at the boundary it has to be 0. So V should be minus V naught. Or the other way around. V naught should be minus V. Yeah, these are the questions I have from previous week. So I also want to show one more problem. So if you want to implement it in a code or something, so let's say we'll take a problem like this is something you are already familiar with, a venturimeter. So you have something like this, and some flow is happening. For now, we will assume it as a 1D flow. Okay. So assume a 1D flow. So what I mean by 1D flow is you already know that whenever there is this wall, you have some boundary layer development here, there will be some boundary layer development here and so on. But what I'm saying is there is no variation along the y direction. So if this is y and this is x, you are assuming only flow along x. Just to kind of, the idea is only to illustrate how to implement simple algorithm by yourself. So if you assume flow only along the x direction, then my governing equations will be, continuity equation will be d dx of u into a should be 0. Like that is what the first equation is. U times area is constant. Because it is incompressible, rho you can consider rho to be 1 or something. And then we'll have the momentum equation just like before. So we have d dx of, okay. And then our boundary condition is u equals to some constant 0, and on the other end we will say du dx is 0. And for pressure, velocity, if velocity is specified, then pressure we do not have to specify anything. So we basically say dp dx is 0 at x equals to 0 initially, and the other side we can keep p equals to some 0, or you can keep p equals to p atmosphere, whatever. Like it's only the pressure gradient that matters. We need some pressure to be fixed. This is one point that we will refer to again. So if you do not specify pressure at any of the point, what happens is in your pressure correction equation. So pressure correction equation is a Poisson equation. So you have something like del square p prime equal to some f. So this is the equation they are trying to solve. And what happens is, say if you use some central order difference, central difference scheme. So you'll have a tridiagonal matrix here that you are trying to solve for. But if for suppose, if pressure is not specified at any of the boundary, what that means is all the diagonal elements will actually, like if the only if the pressure is specified at some point, p prime will be 0 at that particular point, and only then you'll have a diagonal element of 1. So if you do not have a diagonal element of 1, then this basically everything will become 0 and you will not be able to solve this system of equations. So in order to make this solvable, you have to ensure that pressure is specified at least one point in your domain. So what we usually do is we usually specify at least the outlet or something. Wherever you have outlet, you will specify the pressure there so that you can solve this system of equations. Let's see this implementation also. So the code is written in Julia. So just taken 40 grid points, length as 3 meter, density is 1, just for simplification. All these are just for simplifications. U in is 1, and this alpha and alpha p are the under relaxation parameters that I was talking before. So because we are making some assumptions, we are not solving the equations directly. We have kind of made some simplifications by assuming some quantities are 0 and so on. So if I directly use the values, I'm kind of over predicting than what the actual value is. Because I've neglected some terms, the value that the equation directly predicts is higher than what it truly is. So we have to artificially dampen that. So we have to use an under relaxation for both the pressure and velocity terms. So though that is what these alpha terms are. These are again straightforward. Dx is basically L by N. And now we have two different kinds of cells. One is for the phase centers, the other one is for the cell centers. Cell centers will be from dx by 2, like phase centers will start from 0, but cell centers will start from half the cells, half center, like dx by 2 to L minus dx by 2. So this is just to take care of those two quantities. Duct area, I've given some function. as some function here. You can change it to anything else. Now we have two different quantities, center and the area calculated at cell centers and phase centers. I don't think we will use cell center values, only the phase centers is required. So these are just some initializations. So we're just taking u. So again, here comes again, as we are starting, whatever velocity value you are giving in the initial step is only used to calculate your coefficient matrices, but it is not used, like you will immediately update it based on the pressure field. So it is the pressure field is what matters for simple fuzz in the first iteration. So I've specified the velocity to be constant throughout. So u in is basically 1. So I'm saying initially the velocity is constant throughout the venturi. P I've assumed to be 0 everywhere. There is no pressure gradient, but that keeps developing as the iterations go on. D is the coefficient that we'll use in the pressure correction equation. So we have u prime equal to minus d times delta p and so on. So d is that coefficient term. Q is the volume mass flow rate that is kind of fixed in this particular problem. And these are the simple iteration steps. So first, as I said, you have to compute the coefficients, and all these coefficients should be calculated at the previous velocity step. So u old is the previous velocity from which all these values will be updated now. So mass flow rate is u rho times u times a. Rho is basically 1. U times area. This for the west face, east face. Diffusion is mu Ka times by delta x, gamma a by delta x. Where here in this particular problem, gamma is my mu. So this is mu times a by delta x. Now here, this you also recall, so this is in the upwind scheme. When we are using upwind scheme, so max of minus Fe comma 0 plus D. This will ensure that when the flow is in the positive direction, you have the term Fe plus will be there, or the Fe minus accordingly it will change. And this is where we have the relaxation also taken into account. If you compare this particular problem with the scalar transport equation, as we started out here, so yeah, so the scalar transport equation, this is basically my scalar transport equation. If you assume that u is known from the previous time step, and the other u here, the product has two u's. The second u is basically my phi, the scalar that I'll be solving for. So this will be d square phi by dx square minus some source term. So this is basically my source term. So that is a source term that will get added into my b term. Once I have all these coefficients, d is basically a by an, which we already solved, and I am adding this extra coefficient. This is kind of to prevent similarities. If for some reason ap becomes 0 because of the problem you gave, then this will become infinite, and then that will give some errors. So just to kind of prevent that, I add some small term here. So the first step in simple is you have to calculate or update your u based on the p. So that is this first step. You calculate your u star. You just do a Gauss-Seidel update, nothing else. This is just, I've done only one step, but you can directly solve using TDMA or some other algorithm, which will be way faster than this. And again, I also did only one Gauss-Seidel step. Like you can do it till convergence or so, but I've just done one just to kind of make it fast. Once you have U star, you have to update your pressure. So that is where the pressure correction equation comes. So in the pressure correction, again, you have to calculate AW, like AP P prime is sigma A and B P M prime plus P, where the sigma terms are rho times D times A. This is consistent with whatever is the notation followed in the lecture videos. So that I'll share the code with you so you can also try out yourself. So for all the values for I greater than 1 except for the boundary cell, you have the AP calculated from like AW and the other way around. BP for the pressure correction term, the RHS is basically the net mass flux. So why are we doing pressure correction is to make sure that the velocity is divergent free. So the B term on the for this equation will be the divergence of the velocity field. So this is the net mass flux imbalance that is happening across the cell. So once all we have to do is solve this equation, which is AP by B. This solves a set of equations, and I'll get P prime. Once I have P prime, then calculating U prime is straightforward. It's whatever velocity I have plus this is the correction value. U star is the previous velocity plus U prime is basically di times del P. Del P is Pi prime minus this one. So this gives me corrected U. And similarly, I can correct my P. As I said before, for correcting P value, I'll not use directly this one. I'll use some kind of under relaxation, some alpha P times PP. This is because while calculating P prime, we made some assumptions. We neglected the contribution from the neighboring terms. So the value of P prime that I actually get will be higher than what is actually possible. So I have to under relax it, artificially dampen it somehow, and that is why we use an under relaxation factor here. And then now I have to know how long to iterate this. So the convergence step is the mass imbalance step. So I what this BP vector is basically the mass imbalance that I am having here. So if the mass imbalance becomes zero, you stop, or instead of zero, you put some tolerance and then check for the tolerance. The tolerance here is set around 10 power minus 8 and so on. You can solve this. Yeah, so this is the area function that I have taken. You already know as the area of cross section decreases, the velocity has to increase, pressure has to decrease. Like whatever is the pressure drop here is getting, the pressure head is getting converted into your velocity head. Like this we already know for eventually. This is just kind of a cross section. Yeah, are there any questions? Okay, these are the problems I have for this week. If you have any questions, we can discuss them. And I think today is the last session. We can have one more session tomorrow. If we are having a session, you will receive an email for that. By tomorrow, you'll receive an email, the timings, etc. So if you have any doubts, or if you're not regarding any other thing that we have discussed up until now, you can discuss that tomorrow. Even otherwise, I'll planning to have a short summary of whatever we discussed up until now. Not go into the coding part. If time permits, we'll also see some course of how to do it for an unstructured grid, depending on the interest of the students, whoever is so. Yeah, that's it from my end. Thank you for joining. If you have any questions, then we can take them up, or we can end the session for today. Have any questions? Okay. Since we have time, let me discuss one more thing also. Don't think you have any more questions. So let's say we have another problem. Say we have to solve a natural convection problem for suppose. How would the symbol be used for that? The incompressible only. So the governing equations are, let's say, in the 2D. Say gravity is along the y direction, so no source terms here. plus we'll have in simple, sorry, in natural convection with Push-Smith approximation or something, this will become the source term, whatever is a buoyancy term. I'll just write this as buoyancy term B, which will be delta rho times C times delta T and so on. So this will basically be under some conditions which will not go to, but basically there will be some source term in addition to whatever we discussed up until now, and then we'll have one more equation for temperature. So that will be there will be some constant. It will actually be, you can take rho also on the other side. So now we'll have one more equation. So what will change in simple? Like if you want to implement simple for this algorithm, when you have one more additional variable, transport variable, instead of temperature, it can be phi or any other transport variable that you're trying to solve for. So, and then you have also coupling between these two quantities. So what will change now is you start as usual as before. So you have a pressure field P star that you assume, Q star, V star. Now you also have a T star, like you also need to start with an initial guess of temperature. Then you start with solving the momentum equations first. So from the P star, you'll update your let's say they become U double star and V double star. Again, this here, while you're doing this, you're assuming the T here will become T star. So whatever is your previous guess, that will be the value of T star here. So with that assumption, you'll update your U star, V star to U double star, V double star. With the new updated values, now I have to ensure that this will satisfy my continuity equation. So I'll do my pressure correction equation. So I'll have to solve my pressure correction equation, which is del square P prime is minus del dot U double star. So this I'll solve for to get P prime. And once I have P prime, I have the equation for U prime, I'll get U prime. And from this, I'll get new values of, I'm not writing V double star, but you'll also get velocity and pressure. I'll just write it for sake of clarity. So now these velocities and pressure that you're having, this velocity will actually satisfy my continuity equation. So this is a divergent free solution. Now that I know this is a divergent free solution, this U double star and V double star will be used in the last equation. Maybe I'll write update T. Like it is T star to T double star using fourth step is actually straightforward because you know how to do this thing. If velocity is already specified to us, we discussed in the last week. This is a linear equation. All you have to do is you just have to expand it and it will become at equal to some t. Just do the inverse and then you'll get this thing. Update t star. Once you have the new t double star, then again you start check for convergence. And then you just, and if it not converge, repeat from 1. But now instead of P star, U star, V star, you have P double star, U triple star, V triple star, and T double star. And then again the loop repeats. So the only step that is changing here, you'll wait till you get an updated velocity which is divergent free. Use that updated velocity and solve this linear equation. Update the new value of t. If for suppose you are solving another problem where you do not have this coupling, where you do not have explicit dependence on the last variable you are solving. So if the coupling is not present, then it is straightforward. You only solve these 3 equations first, get the velocity, use that velocity to solve the last equation. So this fourth step will actually come out of the loop if you do not have this coupling. So only when you have natural convection this problem comes. But if you are solving a forced convection problem where this effect of this is negligible, or when you are Reynolds number is very high compared to Rayleigh number or something, then you do not have to do this coupling. All you have to do is solve these equations first. Do not worry about step 4. So basically step 4 will get shifted outside the loop. You solve the momentum and continuity first, get your UV, use that UV to solve the temperature equation, and that's it. That will solve your problem. And then what else do we have? Yeah. And then there are other concepts. The next, so people who want to extend from here, the other concepts that you should be looking at is unstructured grids. So the main challenge, the first challenge that you'll get is up until now, let's say you have a grid domain like this. Let's take a simple case. Let's say these are the cells that I'm having. So this is my current cell. This is my I+1 cell or so on. Maybe use different notation. Let's say the same notation. This is my P and this is my E. So now, do you see the difference here? If I join the cell centers, the angle between them is not equal to 90 degrees. So let's say you have a non-orthogonal grid. When you depending on the geometry, this will actually change. So when you have a non-orthogonal grid, then there will be some additional terms that will be coming into your equation. So how will that affect your solution, etc. is something that people who want to move from, like extend from whatever you already learned in the course, you can have, the next step would be to go to this. Here the idea is, again, you define some coordinate system, different coordinate system along this one and perpendicular to this one. And then there will be some additional source terms that will be coming. You have to make some approximations. So here I do not have, how do I define a phase center here? Let's say this is my phase center. How do I compute the value of the phase center? Let's say I want to calculate UE or something at this particular phase, or some other variable, some phi that I want to calculate at this particular phase. How do I do that approximation? Like, of course, you take arithmetic average of all the neighboring cells or something like that. There are other combinations also. How do you do that approximation? That would be one thing that you can extend it to. And then the natural extension is what happens when you have, again, this is how do you store it in the first way. So let's say you can have something like this. Like any point can have an arbitrary number of cells. So this particular cell can be surrounded by multiple cells. How do you know how do you know the connectivity of all these cells, and how do you update it? The general equation will still remain the same. APVP is going to remain as same. This equation is going to remain the same. And even the coefficients are going to remain the same. So we'll have an A and B terms, let's say A east or something, is going to still remain the same. Something like D east minus, let's say if you're using F east by 2. But then this won't be just F east by 2. You'll have contributions from all the, so for example, if this is my cell, this is the normal term, but now because you are having an angle that is not equal to 90, you'll have some contributions here. How are those affecting this A thing? And once your coefficients are affected, the next question is, how does it affect my stability of the solution? So that is, how does it affect my Scarborough criteria? So if you recall, we discussed this last week. So whenever you have an equation of this form that you're trying to solve, you have to ensure that, there is diagonal dominance, so that you have this less than or equal to 1 should be satisfied for all the cells, and it should be strictly less than 1 for at least one cell. These conditions have to be satisfied. Now, once you have an angle that is not equal to 90, there will be some additional terms that are getting included in my coefficients, and that can make this criteria not be satisfied also. So that is one of the reasons you have to have, there are limitations on how much orthogonality you need to have for your mesh. So that is how meshing affects the solution accuracy and so on. These are all the extensions that you should go to once you complete the course. Like, this is the last session for this particular course. So next session, if you want to extend into the next case, you can look upon how these things are getting affected, how these affect your mesh and so on. Yeah, then yeah, these are the natural extensions. And then there will be coupling with other physics, which we will not discuss, which is again another extension that you want to go to. Yeah, but these are the pretty much the immediate extensions are how do you shift it to unstructured grids, because we only discuss structured grids in the entire course. So unstructured, when you have multiple neighbors, how does this thing affect? And unstructured, when you have non-orthogonality, then how to kind of handle that non-orthogonality. So these are the two things that are the natural extensions of whatever we discussed up in the course up until now. Yeah, so yeah, that's it from my end. So if you do not have any further questions, then I think I will end the session for today. Thank you for joining. And if you have a session tomorrow or not, you'll receive an email regarding that. And if you have any doubts, we can discuss that tomorrow also. Thank you for joining.